iRIC has various solvers. When choosing a solver, the first thing to pay attention to is the spatial dimension. Among many 2D solvers, NaysCUBE is a 3D solver.
3D solver require more CPU time than 2D solvers. Therefore, computations for a long reach of a river is not recommended. This solver is suitable for reproducing a bend in a river, flow around river structures, secondary flow in a cross-section, etc.
NaysCUBE employs general curvilinear coordinates for the horizontal direction and sigma coordinates for the vertical direction. It is possible to create grids that fit complex terrain, and it is suitable for three-dimensional calculations such as actual rivers and artificial waterways. In this solver, physical space with generalized curvilinear coordinate is transformed into computational space with Cartesian coordinate composed of cubes with a side length of 1. This is where the name NaysCUBE comes from. Fluctuations of the water surface are calculated by the boundary-fitted grid method. It is possible to consider submerged and emergent obstacles and vegetation on a cell-by-cell basis. Underpass-type structure also can be considered. This is an example of a calculation that reproduces the flow around a structure with an underpass on a movable bed. Compound river channels and submerged weirs also can be considered by using these kind of grids. In general, creating a 3D computational grid is a very time-consuming and complicated task. But don't worry, NaysCUBE requires only a plain two-dimensional grid. The vertical division is done inside the solver. Various boundary conditions such as periodic boundary conditions, symmetric boundary conditions, etc. can be easily set in NaysCUBE. This is one of the major advantages of this solver. For periodic boundary conditions, the condition at the upstream end is always set equal to the calculated value at the downstream end. This makes it possible to calculate an infinitely long periodic phenomenon in only one interval. In the inverted periodic boundary condition, the calculation result at the downstream end is horizontally reversed and given to the upstream end. This makes it possible to calculate the reversing periodic phenomenon in only half the period. Periodic boundary conditions can also be applied in the transverse direction. It can be used when there are bridge piers or dunes evenly spanwise direction in a wide river. Symmetric boundary conditions can be used for transversely symmetric flow fields. All physical quantities are given symmetrically with respect to the center axis as if projected by a mirror. This expresses the phenomenon of a dense and uniform vegetation area only in a unit area by combining several boundary conditions. Inverted periodic boundary conditions are used for the upstream and downstream ends, and symmetric conditions are used for the left and right boundaries. In the computational result, we can see complicated unsteady flow structures and bed deformation. The turbulence model is the heart of the 3D model. A RANS-type model is adopted for this. You can choose from linear, second-order nonlinear, and third-order nonlinear K-epsilon models. The scheme of the advection terms, which greatly affects the calculation accuracy, can be selected from 3 types: first-order upwind scheme, quick scheme, and third-order TVD muscle scheme. For the morphological computations, NaysCUBE can consider bedload and suspended sediment. The bedload flux equation can be selected from Mayer-Peter-Muller model, Ashita-Mikyu model, and Kovach-Parker model. In the suspended sediment model, the Euler-type advection diffusion formula and the Itakura and Kishi model for the standard density are employed.
I'd like to show some computational results with NaysCUBE. This is a computational result at a river bend. You can see a spiral flow. This spiral flow is called the secondary flow of the first kind. It causes deposition near inner bank and erosion near outer bank like this. The secondary flow is also generated in a straight channel and is called the secondary flow of the second kind. This flow induces the wavy bed form in the lateral direction like this. Recently, driftwood disasters occur frequently in many rivers. NaysCUBE has a function to simulate driftwood movement. In NaysCUBE, driftwood is expressed as connection of element spheres. Once, each sphere is advected independently, and then, the disordered spheres are rearranged again in a row. Repeating this process step by step, we can simulate the continuous movement of driftwood. The collision of driftwood pieces each together is modeled with the discrete element method. This is an example of computational result of driftwood movement in a river. The motion of arbitrary shaped floating bodies can be easily reproduced by arranging element spheres on the object shape. NaysCUBE also has functions to calculate considering dams, gates, winds, closed water basins, pumps, etc. This is an example of simulated submerged driftwood motion in dam reservoir.
With the recent diversification of disasters and the increasing demand for river environments, the need for 3D computation is increasing. We hope that you will use NaysCUBE as a tool that allows you to perform 3D calculations easily, enjoyably, and free of charge.
Thank you for listening. Yes, 3D. Enjoy computations with NaysCUBE.